Hey Wheat North, Mr. Yergler here. Let's talk about oxidation reduction reactions. We've actually already covered this. It's all the way back in Unit 1. I'll put a link to that video that goes in kind of in more detail and more depth. So I'm going to kind of fly through a few things in here, so it might be helpful to go back to that video. So oxidation is going to be when electrons are lost. If you have carbon +2 going to +4, these are oxidation numbers. They're not necessarily charges. They're not quite the same thing, but they're kind of close. But if it's going from +2 to +4, it's getting more positive, which means it's losing a negative electron, actually 2 electrons, right? So that's being oxidized. Something that's being reduced is going to go from a positive number to either neutral, or the charge is going to get smaller, right, or more negative. And so in this case, iron +3 to iron with no charge is going to be a reduction reaction. This is actually where the name comes from. It's a really confusing name. I like to use this mnemonic oil rig to remember that oxidation is loss of electrons and reduction is gain of electrons. The reason that we call it reduction when we're gaining electrons is because this started way back in probably the Bronze Age, when they first started turning iron ore or other metal ores into pure metals. The iron ion would be in a compound, like an oxide compound probably. When they put this in a huge furnace, the mass of it would be reduced because it'd be going from iron oxide to just iron. They had no idea what was going on, but they called it reduction. And the name has kind of stuck, and so now we're stuck with that name. So if you want to think of reduction in charge, that works. Or you can just remember that reduction is gain of electrons. Gain of electrons would be a reduction in the charge. And these always happen simultaneously. So you can't really have an oxidation reaction that doesn't also involve something else getting reduced, right? Because those electrons have to go somewhere. So if electrons are always lost, they have to be gained by something else, right? So if something's getting oxidized, something else has to be reduced. And this is where we come to half reactions. So here's a typical single replacement reaction. Actually, every single replacement reaction is an oxidation reduction reaction, because you're always going from a solid metal to a metal in an ionic metal in some sort of compound. So I'm going to rewrite this as a net ionic equation. We have 2 nitrates on both sides, so we're going to ignore those. Those are spectator ions. And let's change the colors of these so that we can kind of keep track of what's going on here. The zinc is going from 0 to +2, so it's losing electrons. And the copper is going from +2 to neutral, and so it's gaining electrons. And so from here we can write half reactions. The oxidation half reaction would be zinc to zinc +2, and we just kind of narrow it down to just what's happening on the oxidation side of things. The half of the reaction that's being reduced is the copper +2 going to copper metal, right? Solid copper metal. Anytime you see a solid, it has a charge of 0. Now what's happening with electrons? Well, in reduction is gain, and so we would add electrons on the reactant side in that case. Oxidation is losing electrons, and so they can be thought of as a product. So they're lost by the zinc and they're gained by the copper, the exact same electrons actually, if this is happening kind of all in one container. We have to be able to keep track of where these electrons are going, and so we assign what's called oxidation numbers. Sometimes they're referred to as oxidation states. And here's a simplified set of rules for that. Again, more detail was given in a previous video, but essentially they all come from these first 3 rules. Elements and ions always have the charge of that element or ion. So if it's just an element like chlorine, it would be 0. If it's just a monoatomic ion like sodium ion, or in this case sulfur ion, it would just be equal to its charge. Kind of similar to that, the sum of any neutral compound has to be 0. So if you think of 2 hydrogens and 1 oxygen in water, those oxidation states of those atoms have to add up to 0. And kind of similar to that as well, if it's a polyatomic ion, they have to add up to the total charge, to the charge of that polyatomic ion. So sulfate, SO4 - 2, has to add up to -2. Here's a couple more guidelines that are helpful. It's important to remember that halogens are pretty much always -1, oxygen is pretty much always -2, and hydrogen is pretty much always +1. So that kind of helps us with figuring out what's what. Let's look at an example. So let's assign oxidation numbers for every element in this reaction. It's easiest to always start with oxygen because we know that oxygen is going to be -2. The iron is what we don't really know. Now there's 3 of them, so that would add up to a total of -6. The whole must add up to 0 because it's a neutral compound, and so the ions must add up to +6, which means that they're each +3. With the carbon monoxide, the oxygen, as always, is -2, and so the carbon must be +2. The iron is just iron, it's elemental, and so it's going to be 0. In the carbon dioxide, oxygen is -2, and there's 2 of them, so that's -4. So then the carbon has to be +4, and there's only 1 of them, so it's +4. So this allows us to keep track of what's happening with electrons. Iron is going from +3 to 0. It's the easy way to identify what's being oxidized and what's being reduced. So what would be the half reactions? Go ahead and pause the video and write those down. The oxidation half reaction is going to be carbon monoxide going to carbon dioxide, and I left the 3's in there. A lot of times you would see this probably without the 3's. And the reduction half reaction would be the iron oxide becoming iron. Anytime you're going from a metal compound to the pure metal, it's always going to be reduction, right? Think about that blast furnace, purifying a metal from its ore. So the reverse could also be true. Anytime you're going from a solid metal to some sort of compound, it's going to be an oxidation reaction. Now notice something about these half reactions. They're not really balanced. For example, oxygen doesn't appear on the product side at all. We're not saying that the oxygen is disappearing. Remember, it's a half reaction, so it's only representing half of what's going on, right? So you'll often see them in where things aren't balanced, and that's just kind of how they're written usually. We can balance half reactions. We've done that before, and we'll do an example in class, but you're pretty much always going to be given balanced half reactions on like the AP exam or a situation like that. So that's a quick review of redox reactions. You need to be able to identify if a reaction is a redox reaction by tracking oxidation numbers, and identify what are the half reactions for the oxidation half and the reduction half. If you have any questions at all, of course, as always, bring those up in class. And this is Mr. Yergler signing out.